Uh, a couple of comments. This construction is only on 0, n squared intersected with z2, zd if you want. Whereas we want a field of arrows in Busemann function functions on Z2. So the idea somehow is to go back to this picture and you fix this point, I'll call it Zn, and say it goes off to infinity, as in absolute value, and Zn over Zn goes to some alpha, and then you look at these differences of the form T a comma Zn minus T a minus Ei comma Zn. And then I'll put in an alpha here and say, and you ask if this goes to some limit as n goes to infinity, to some b alpha, a minus e. So there's a theorem that says following. This is due to Dameron Hansen in 16 and Alberg Hoffman. I'm not being completely precise, but more or less, if alpha is a direction where grad mu of alpha exists, the differential, so it's a direction of differentiability. Then B alpha exists. It's stationary, it has all these nice properties and so on.
Can you scroll up a little bit so that I can see what B alpha was? I see. So it's this limit of B alpha.
It's a and B alpha exists and is a Busemann function having all these nice properties. Of course, the key here is that this is unknown. This is open. Okay. So what could go wrong? So if your direction alpha, I'm drawing it this way, it doesn't matter so much. If this is my direction alpha, I have a derivative, then the Busemann function exists, and with a little more you can even show it's unique and so on. But if you have some sort of corner, so this is my limit shape, boundary of my limit shape. If there's some corner like this in some direction alpha, then we don't know. Okay, so now I have to make a connection back to from these Busemann functions that I've connected and the KPZ behavior in D equals 2. So recall conjectured KPZ relations. 2 chi minus 1 equals C and 2 chi equals C and D equals 2. If B alpha 0, say nx, goes like some constant times x plus with random fluctuations that are like this, sigma z diffuser, then this is supposed to hold. And this is probably one of the main open questions in this paper. Open and important because of this KPZ connection, which is connected to all these other questions about random matrix theory. And so. Okay. So somehow, yeah, the existence of Busemann functions, you want to use them as a tool, but whether they exist or not is related to the time constant. And well, the original question is, can you show this time constant is smooth? And if it's smooth and curved, then you have geodesics and so on. So they're all tightly interconnected. So if one of these falls with some new techniques, then one should expect many of these questions to be answered. We don't know any of these. Okay. So I've listed several connections for these Busemann functions. So Busemann functions, just to sort of summarize, they're connected. They come from metric geometry, but they're related to this KPZ relation, existence of bigeodesics connection, and also connected to this constructing families, compatible. So now I want to somehow focus on this and study it kind of abstractly. So going back to this picture where I have all these arrows, I could say, forget all this Busemann function stuff. I'm just given some system of arrows like this, one at each point and so on. So my space would be omega, which would be here I've just shown E1, E2, or minus E1, minus E2 to the ZD. There's an arrow at each point on the lattice. Each point. And then I have some measure on omega. That's some translation invariant or stationary. Stationary, and by the ergodic decomposition, you can also assume it's ergodic. Okay, so this is my setting, and if I'm given this setting of arrows, I can construct flow lines of the arrows and obtain a family of compatible walks. We'll call that this x sub z, z in z2. Oh, no, I can do it in zd, but let's focus. Actually, I'll do it right. Okay. So my question is, what sort of behaviors are possible? So in the FPP with IID weights case, we saw due to Lecce and Newman that geodesics must coalesce almost surely. And bigeodesics cannot exist. This is indeed ghost. Okay, so this is quite a general setting. So there are many possible sort of measures that can be stationary and ergodic. So it might seem a little hopeless to sort of classify all sorts of behavior. Okay, so let me give you an example. So I'll let omega be a 2-point space, omega 0 and omega 1. And I'll make my arrow assignment periodic. Okay? So if this is my origin, I'll put my first arrow here. And then when I go up here, I'll put my second arrow go up there. And I go up once more, my arrow will go here. Go up once more, my arrow will go up, and so on. Can go up here, I'll get an arrow there. I'll go up there, my arrow will go here. And will go up there, and so on. I'm just periodically assigning these arrows.
So these arrows are meant to be on vertices, right? In some sense.
Yeah, each vertex has an arrow. Is which way is your walk going to go out from it?
So once it's like a ramp. Once you're on it, you have no choice. You just keep on following.
You keep on following.
The only choice I have is where do I start? That is the only.
That's the only choice. But what I'll do is I'll form a walk from every point on the lattice, and form these.
And then it's these ramps which have been prepared.
Sort of precast on the lattice. So, for example, you can see these flow lines here. These are my flow lines. So this system you can show is stationary and ergodic. And you can see these bi-infinite trajectories clearly forming. So these are bi-infinite trajectories.
So this would happen in any periodic configuration.
I'm not sure, but should, right? I don't know. Not
because
immediately
you won't
obvious.
have coalescence in. So if you have any periodic trajectory, this is a factor of that. So you should not have coalescence because the coalescence should repeat periodically, and then I think you'll have the same problem like you have with key, working key. So it should just be all parallel all the time for any periodic choice. Or okay, something different.
Possibly, yeah. Possibly, yeah.
In case you just go up and right.
Okay. So you have these bi-infinite trajectories. Nishant asked a good question. Is it if do you form these bi-infinite trajectories always? You form.
I'm just talking about the periodic.
Yeah, bi-infinite trajectories.
And I think there it is. It seems to be true.
And it is always.
So you're saying any periodic one will, you're saying that should be the case.
I'm not sure.
Yeah. Okay. Hold on. Yeah, I think you're right, but anyway. So the question is, do bi-infinite walks exist? Yes. And second question is, what about coalescence? let me show you another sort of extreme example. In this extreme example, I just flip a coin and assign arrows in some IID way. I go up there, maybe this is up again, and maybe that's up, and maybe that goes right, and so on. Goes right, goes up, and so on. Sort of IID arrows. So in this case, if I start walks at two different points, I call this SX, and I call this walk SY. If I tilt my head sideways, these are two IID random walks, at least until coalescence. Here, can you guess what happens?
Two random walks, two dimensions. Now it depends. If you're in 5 dimensions, you don't.
Yeah, in D equals 2, they coalesce. So. Two. So we've seen these two behaviors. There could be other behaviors, like say, for example, you have, one tree like this, a coalescing tree. You could have another tree like this. And the question is, can you have many trees? Many such trees. So let me tell you what happens. So this is John Chaka and myself. It says, in such arrow systems, one with probability 1, x sub z and x sub y coalesce for every z comma y and z2 equals 2, or there exists by infinite walks such that no two such walks coalesce B, all other walks must coalesce with the bi-infinites. There must be infinitely many bi-infinite walks. And T walking along bi-infinites preserves measure. I'll leave that a little loose. Preserves measure.
Infinitely by infinite walks, they don't walk. They are all parallel.
They are all parallel. So the picture you must have in mind is something like this, and then all the other things must coalesce with it. All the little baby walks must coalesce.
They cannot. The other ones cannot coalesce with each other. They have to coalesce on one of these.
They can coalesce with each other,
Oh,
but
okay.
Eventually they must coalesce.
Eventually.
So they can't be just one-handed tree also. It's only by infinite parts.
And so this point D, I've sort of hidden lots in this But this is very powerful. For example, it tells you that these bi-infinite walks must have asymptotic direction. Because of the ergodic theorem. You can ask, how many times do I see a right arrow? There's a density. How many times do I see an up arrow? There's a density by the ergodic theorem. And so there's some asymptotic velocity.
So when you say walking along bi-infinite paths, is this just some kind of TT inverse kind of thing where you just look at the point, look at where the arrow is pointing, and then you just translate along that direction?
Yes.
And that is defining a transformation on your space of arrows.
Right.
And
it's a Z action.
It's a Z action. And so this is right. So but this, once you have a space of arrows, it automatically defines for you some such TT inverse, some such skew product.
Right.
And
it won't be invertible because if they coalesce at one point, then
right. So you have to. So that would be make it an N action, I guess. The semi-group action.
Yeah. But so what could happen is that so if you have your big space omega like this, there's a subset of bi-infinite trajectories, and then there the action is invertible, stationary, and so on. But in the coalescing case, somehow if you have a big omega, they can all sort of coalesce into some really small sort of some fractal subset of your space. So it could have some terrible attractor or something.
So you actually have a, I see. So the action is that of the group N actually, in fact not Z, right?
If you think of a semi-group, yeah. In the coalescing case, but it becomes a Z action.
A Z action if you have any bi-infinites, I guess.
Yeah.
By your theorem.
Right. And okay, so what's open here, I should say, is show me that they're all equivalent in the sense of a distribution. Show me all bi-infinite trajectories are equivalent under appropriate law. Okay, so this in ergodic theoretic language, this would be showing walking along. Sorry.
Non-singularity. Just their equivalent.
They're equivalent. It's equivalent to say that they're just ergodic. That the measure they preserve. So show me it not just preserves measure, but this action of going along. The measure is also ergodic for this action. So you can see sort of shadows of this theorem in interacting particle systems and so on. From when you look at point of view of the particle, then one particle is equivalent to the other. That's the theorem of Ellensada and so on. And so, question is, give me some nice description of randomness on my arrow system and show me that they're equivalent. Then if you can do that, then I can in fact, tying it back to Busemann assumptions, show there exist Busemann functions without assuming anything on the shape.
Then KCZ will also follow?
That would require more.
No.
It's harder for sure. That requires showing the Busemann functions are diffusive.
Oh, okay.
So, yeah, there
existence is
not enough. There somehow you really need to use IID somehow.
Right. So when you, so which generality are you? So you have told me what generality you are aiming at.
Yeah. In the sense that
give me a class which you would love to know it for.
So there's a function f of omega that maps from. So I have my general setting. I would say is omega is R to the Z2, and I have some product measure is mu is my, you know, and I have some function on omega to, you know, E1, E2, space of arrows. Um, uh, Question: if by infinite geodesics exists, by infinite walks exist, are they equivalent? Are they equivalent? Um, yeah, it's a little loose. There are more constraints on this. It's a very sort of constrained problem because yeah, I don't know. Maybe there's an easy counterexample too. Maybe it's too much to hope for. Okay, so you can say a lot more about these things, but I thought I'll end with a question and some yeah, and all of these connections to Busemann functions.
So the description that you have given right now is just of IIT.
Yeah,
So
just
that's where the questions
yeah.
for you is the most interesting.
That's the only question, and yeah, I was, you know, all these other ergodic theoretic things are nice to have, but
Sure.
not essential. Just IID. So, okay.
So a lot of this also. Oh, sorry. Yeah.
Maybe we should stop and then we can talk afterwards, or other.
We'll ask if so there are questions. So okay. So firstly, let's thank Arjun for wonderful presentation. We have time for questions. Oh, sorry. So we have time for questions. If anyone from online wants to ask. Yes, go ahead, Nisha.
Yeah. So most of I might have missed something very elementary in the beginning, so sorry if I'm asking some. This is mostly in the setting of last passage percolation, right? This is because you are directed percolation, one of the two settings.
Yeah.
That is. And if you want to somehow talk about similar things in first passage percolation, then there's of course the issue that you might have many multiple. You might have, like here at least you're going up and right, but if you're thinking in terms of first passage percolation, then it might be.
It might swirl around a little bit, but there too, if you have some property of the limit shape, say
The differentiability,
or something
convexity.
They at least in D equals 2, you can trap things and say they cross planes in some sense. So a lot of those, there are difficulties generally when writing proofs for first passage, and that's for looping back for sure, but they can be handled more or less.
The last year, basically,
This theorem I stated? No, it's just for arrow systems. Some stationary measure that says wherever you move on the lattice, the measure is ergodic. Yeah, but you can assume stationary, but
if it is added, then the first one will become true, right?
yes, that was the example. That's right.
I mean, so this Busemann functions, maybe I missed something. So, is it what is it useful for? I mean, you rephrase, for example, the KP in this form.
Right.
But is there something you prove using Busemann function? I mean, I don't know.
Is there something concrete you can prove? Yes. So they were originally used by Hoffman. So this question of are there infinite geodesics without assuming anything on the shape.
Okay.
So you can show that there's at least one or two by Chris Hoffman, and that uses Busemann functions in an essential nice way.
I see.
and then he extended it to 4, and I think state of the art is maybe 8, but the conjecture is that there are infinitely many.
So in 2 dimensions, so far you have 8.
Yeah, 2 dimensions.
Okay, so there you do use.
You do use this.
I had a more question about the last one. So I don't have any intuition why you can't have bi-infinite geodesics and also these one-ended trees of geodesics. Or is that?
Um, it's not so easy to explain intuitively, but again, it's a lack of space argument in some sense. So basically, you say that. Okay, so loosely I can say this. Say, suppose you have 2 points that never coalesce. We are in some directed setting. And then in some sense, you'll have, so as long as you find 2 points that don't coalesce, in a larger box, you can always find, you ask for geodesics or points that carry geodesics with K history. And so you'll show that these two densities are related, the densities of pairs of points that don't coalesce and of points that have K history, meaning you can walk K steps backwards. And then you show that in fact this probability of K history is lower bounded by the probability of these existing, it's independent of K. And so then a little massaging, you can send K to infinity and show the correct point. It's okay, little, yeah.
Maybe I at least get some intuition. Any further questions? Okay, so if not anything online, so if not, then we can. So thanks again. So the recordings are will be put on the IAC department website, also linked from PPS website.
Shrikar has a question.
Oh, okay. He's muted.
He said someone had asked in the beginning about the role of ZD in this. Can you elaborate a little bit on the question? Was that you?
I think I just made a comment that the Burton-Keane argument, general extends to amenable groups, and whatever you showed seemed to be just seemed to care about box boundary and so on.
Yeah, yeah.
So it was just an innocent, stupid question. That's it.
But he's asking exactly hexagonal lattice. So how much does changing lattice change anything? Maybe that's the question.
I don't think it'll change it by much. No, I think it can be generalized.
Nothing.
Yeah.
Like I guess you just need some directionality.
Yeah, and that you impose on your walks. For first passage percolation, certainly the limit shape will change. It depends on the lattice. But these sort of general theorems about geodesics, it won't matter.
This is